All right, so let's go ahead and begin again. If you remember last time, we were talking about how substituents on the benzene ring affected two things. First was the reactivity of the ring, and the second was the orientation, how the substituent directed the substitution of an electrophile. And we looked at the effects of single substituents, and then we talked at the end of the lecture about what happened if you had more than one substituent and how we looked at how each substituent could direct either to the same site or different sites. And we talked about how the stronger the activating effect is, that's going to be the one that leads to the major product. And so what I wanted to start with today is to look at how that actually affects a synthesis problem, because we're getting back into that. And so how can those things affect synthesis? Well, what it has an effect on is the order of addition. Because if you're starting a synthesis, for example, from benzene, so remember in a retrosynthetic analysis, we're going to use our retrosynthetic arrow. So what I'm showing here is we're starting with benzene and we're trying to make this compound, where we have a nitro group and a bromine that are meta to each other. Okay, and so how would we go about doing this? Well, what you have to start looking at now is the order of addition. In other words, which of those groups which of those substituents would I put on first? Because whatever one goes on first then directs the substitution of the second group. And so, for example, if we started here with benzene, there are two ways I could do this. The first is I could substitute in the bromine, and that would give me bromobenzene, where I substituted the bromine. Okay, and then if I tried to then follow that with nitration, where would that bromine direct the nitration? It would direct it ortho and para to that bromine. Would that lead to the proper product? No, because the nitro group is meta. It's in this position. So I can't add the bromine first synthetically. It would not lead to the proper product. But if I added my nitro group first and formed nitrobenzene, then that nitro group, if I followed that up with bromination, that nitro group would in fact direct the substitution to the proper position, and I would end up with the compound I was trying to make. So the take-home message here is, when we're looking at synthesis, which we're going to do more of probably by the end of the lecture today, the important thing with these electrophilic aromatic substitutions is that when we do a synthesis, the order of addition becomes important. Okay, and so another couple examples just to bring that home, because there may be situations where synthetic utility reactions come into play. Okay, so for example, let's say that I wanted to do this synthesis. It's going to be related to the other. Let's put a amino group there in the bromine. And let's say we want to synthesize that. How would we do that? Starting from benzene. So how would we change our synthesis? What would we do? Well, we look at these two things and they are meta to each other, but neither of these are meta directors. Okay, and so if you remember with the synthetic utility, if we go back one step from this, we could go back to where that's a nitro group. Remember the Clemmensen reduction? So if neither one of these groups directs meta, then we can ask ourselves the question, are either one of these groups something that we can make from a meta-director? And the answer is yes, because this amino group can be made by the nitro group. And once you see that, then you know, well, I can go back because it's the bromine that would be added from the nitrobenzene going back to benzene, because if I put the nitro group on first, it directs the bromine meta and then allows the reduction. So the forward synthesis would be adding the nitro group, substituting in the bromine, and then reducing. You remember what the reduction is with Clemenson's? It's that zinc mercury amalgam and aqueous HCl. Okay, so synthetic utility reactions can be used to help direct things in the proper order. Now, what if you did this synthesis? Let's change the position of our bromine. How is that going to change our analysis of the synthesis? Well, now I have two substituents that are ortho to each other, okay? And they're both ortho-para directors, okay? And I could imagine then going back and saying, if I had this aniline compound, I could brominate it and get this product, because this is going to direct ortho and para. Okay? And so then that would then go back to, well, I can't put an amino group directly on the ring, right? By synthetic utility, I have to make it from the nitrobenzene, which again goes back to my benzene ring. So what would the reaction be here in the forward direction? Nitration, right? And then the zinc mercury amalgam, which is the Clemenson, and aqueous HCl. That gives me this, which I can then substitute using the bromine. So the take-home message, just as a preliminary thing here, looking at synthesis, is the importance of the order of substitution of the substituents, because they're going to direct the next group you substitute, but also the fact that the power of those synthetic utility reactions allows me to change a meta-director, for example, into an ortho-para director. All right, so last time, as we were saying at the beginning of the lecture, we had talked a lot about reactivity and orientation of the substituents attached to the benzene ring. And so now what we want to get to is the explanation for that. I promised that we would get to that. So explanation of the reactivity and orientation. Now, the one thing I'll say before I start talking about this is on Moodle, there is a PowerPoint related to this chapter that I'm going over now, although I'm not lecturing straight from it. You should go look at that, because it has some really good slides that show some of the explanations I'm going to do on the whiteboard, and it'll supplement that, so be sure you look at that also. Okay, so how do we explain how a substituent affects the reactivity and the orientation? We're going to start with reactivity. And remember, with reactivity, we said that it could be affected in two ways. If you go from just plain benzene, if you added a group that withdrew electron density from the ring, it made it less reactive, and if it donated electron density, it made it more reactive. Remember that? And we actually said at the time that there were two ways that that could happen. So that's what we're going to talk about right now. What are the two ways that you can affect the reactivity of donating electron density either into the ring or out of the ring? And the first of those is induction. Okay, and do you remember induction from Organic 1? Induction was what? It's due to the intrinsic electronegativity of atoms and to bond polarity, which is a result of that, in a functional group. Okay? And remember, it operates through a sigma bond. So induction, you have two atoms that are bound together. There are two electrons within that bond. Due to the electronegativity of the two atoms, one of them is going to be more electronegative than the other. If that's the case, the electrons are going to be pulled towards the one that's more electronegative. That's going to cause bond polarity, okay? And it will either remove electron density from the ring or donate it into the ring. Okay, so the important thing to remember is it operates within a sigma bond. And so examples of looking at this, let's say you have a benzene ring and your substituent is one of the halides. Halides are electronegative, so inductively that means I'm pulling electron density away from the ring. And so I'm producing some deficiency in that carbon within the ring because the halide is pulling electrons towards it. So in terms of reactivity, this is going to be deactivating, right? Because it's taking electron density out of the ring. And you can look at an example like this, where we have something that's a carbonyl compound. Substituent has the acyl group. And in that particular case, if you remember, this particular carbon has a partial positive charge on it because of the inductive effect of the oxygen that's attached. So if this is deficient, it actually becomes more electronegative. And it's going to inductively pull electrons from within the ring, and so it's going to make that ring deficient. And you could continue on with this. Another example is a nitrile, where this is electronegative, and so you're basically pulling, almost in a tandem method, you're pulling electron density out of this ring. So all of these are examples of things that are deactivating. One more, because it's important and we see it a lot. If you have a nitro group, okay, this nitrogen was already electronegative, but now I've made it plus charge. Remember, that increases the electronegativity. And so therefore, inductively, the electrons are being pulled away from the ring. So all of these are deactivating. Okay? Not the only ones. Because you can also have inductive withdrawal from things like hydroxy and amino, because same thing, the oxygen and the nitrogen are more electronegative. So inductively, these are also deactivating. They reduce the reactivity of the ring. Okay? There is one example of something that is inductively donating. And that is if you have an R group. And I'll just use a simple example of a CH3. Here, you're inductively donating into the ring. And so that is why an R group attached to the ring actually has an inductive activating effect. And think about carbocations. Remember how we talked about the more carbons that are attached, the more substituted a carbocation is, the more stable it is. That's because of this inductive effect. Okay? So that's one way electrons can be donated or withdrawn from the ring to affect reactivity. The other way is through resonance. And remember, both of these effects can be occurring at the same time. You can have induction and resonance occurring at the same time. Okay? But a resonance effect, it's maybe been a while since we've talked about resonance, but remember, resonance was actually the movement of electrons within a pi system. So it's not, locally isolated to a bond, a sigma bond between two atoms. Resonance, the electrons are in the pi system, so you can have electrons moving through, more than just between two atoms. It can move through a complete pi system, okay, which we said was a stabilizing effect. And so we can say resonance operates by donating or withdrawing electrons through pi bonds, which are p orbitals, of course. Okay? And so when you have, for example, and I'm choosing this first example on purpose, if you have a nitro group attached, remember a minute ago we said that that was inductively withdrawing. This nitrogen is, has a positive charge. The electrons within this bond between this carbon and this nitrogen, those electrons are being pulled towards it, so inductively deactivating. But resonance, we're talking about electrons that are in a pi system. Okay, and so what you can imagine happening here is these electrons, since they're all in a pi system, can move out towards this nitrogen. And when they do that, these electrons move out to that oxygen. And so you can draw a resonance form for this. I've moved these electrons out, right? So I formed a double bond here, nitrogen, O, O. Each of the oxygens have a minus charge because the electrons have moved out to this oxygen. And so what's been left here, that carbon is now deficient. It's got a plus charge. And of course, you can and you will draw the other two resonance forms where that plus charge moves through the ring. And so what would that do to the reactivity of the ring? It is, in a resonance effect, removing electron density from the ring. So that is a deactivating effect. And the simple conceptual way of looking at that is in these reactions, the ring is acting as a nucleophile, right? It's pushing electrons out to the E+. And if you're taking electron density away from it, you're making it less nucleophilic. All right? So that is one example of resonance withdrawal. Another example is when you have your carbonyl substituents. So let's say, just in a simple example, we have this aldehyde. Okay? And so again, you can imagine in a resonance way moving these electrons out of the ring towards this deficient carbon of the carbonyl, which pushes these electrons up. So a resonance form you could draw for this, again, would have a double bond now to this carbon, moving the electrons out to that oxygen. And the result of that is that you form a deficient carbon within the ring. Okay? And then that you could and you will, on a test, draw the other two resonance forms for this to show that in fact you have removed electron density from the ring. And in doing so, you've made it less reactive as a nucleophile. So again, deactivating. Okay? A simple way of remembering substituents that are resonance deactivating is they have a kind of a general formula. Anytime you have an aromatic ring, that is attached to an X and a Y. Doesn't necessarily have to be a double bond, but some kind of multiple bond. If the Y is more electronegative than the X, okay, which would mean you'd have a situation where you have partial charges like this. Any situation like this, and you can go back and review the lecture, just difference between live and digital as you can kind of rewind. You'll see that all of those resonance deactivators that we just went over fit this general equation. Whether that's a C double bond O or whether it's an N double bond O, they all fit into that general formula of resonance deactivators. Okay? So that explains how substituents can be deactivating. Now we've seen both inductively and now through resonance. And they're not mutually exclusive. Something like a nitro group is not only inductively deactivating, it's resonance deactivating also. Okay, so let's look at a little different case here. Okay, we've looked at resonance deactivators, but what about resonance activators? If you have an ether substituent, remember this oxygen is going to have lone pairs on it. So in terms of resonance, this oxygen, this does not fit that previous schematic I just put up, because this oxygen is not deficient, right? It has lone pairs on it. So you could imagine it pushing electrons into the ring. And so a resonance form you could draw for it would look like this. Where now I have, in a resonance manner, moved electrons into the ring. So this carbon now has a formal minus charge on it. And you can and you will on the exam show the other two resonance forms for this where the oxygen is moving through the ring. And so again, just conceptually looking at this, we have now pushed electron density into the ring. We've actually moved electrons in there through resonance. So that's going to make this ring more reactive. And so this is a resonance activator. The exact same thing could be said for any substituent that attached atom has a lone pair. So you can imagine the same kind of resonance occurring if you had an amino group, where I would form this resonance form. And again, you'd be able to show the other two resonance forms for this, where the minus charge is actually resonating through the ring. Okay, so this is resonance activating. Okay, now the general equation then for resonance activators, as I said, anytime you have a substituent where the atom attached has a lone pair. So that would mean looking at something like where you have a Y attached, and it could have other things attached to it. But as long as that Y has a lone pair or more than one lone pair on it, it's going to be resonance activating. Okay? Now, who noticed something as I went through this? I'm going to erase this because I know you can pause and go back and copy that down if you didn't get it quickly enough. And that is looking at an example like this. I'm going to draw this molecule twice. Because when we were talking about inductive effects, we said what? That this was inductively, I'm going to put induction next to this. Inductively, this was withdrawing electrons from the ring. Remember, through this sigma bond, electrons were being moved from this carbon to that oxygen. So we said it was deactivating. Right? Well, just a second ago, we said that through resonance, that this was actually activating. So with the resonance explanation, you're moving electrons into the ring, So that's activating it. So induction and resonance are working in opposition to each other in this case. Remember, nitro group, we just said it was inductively and resonance deactivating. Well, this substituent is inductively deactivating, resonance activating. Well, what did we say about OHs? Are they activators or deactivators? Remember on our table we said they're actually strong activators. So what does that tell us about these two effects? And this is going to make perfect sense. Resonance, you're actually moving physical electrons into the ring. Induction, you're just pulling electrons within a bond. So a resonance effect is far more, overpowering than induction. So resonance is going to win out. Okay, so if something is resonance withdrawing or resonance activating, it overcomes any of the induction effects. Okay, there is an exception though, and it's the only exception that we talked about. The only exception to this are the halides. So if you look at a halide, it has a lone pair. So these are in fact resonance activators. Because you can imagine drawing this resonance form where I've moved electrons into the ring. Right? Leaving a plus charge there. Okay? But they're also inductively deactivating, where I'm moving electrons through this sigma bond away from the ring. Well, in the case of halides, because they are so electronegative, the most electronegative things, the induction in this case overpowers the resonance. So that's why these are actually deactivators. All right, but they're the exception. Okay. So the next thing we want to talk about, this covers the reactivity, how we affect the reactivity of the ring. And so now what we want to talk about is the orientation. So explanation of orientation. And again, we said it was correlated to reactivity, and it is. But this is going to be a little more complicated because the explanation for this, just like with reactivity, we did use a little bit of mechanism there, especially with the resonance showing the movement of electrons into the ring. But now, to explain orientation, we really need to go back and make sure we understand mechanistically what the explanation is. And again, I encourage you to look at the PowerPoint that has all of the examples I'm about to put on the board that are actually, drawn out schematically. It'll be worth looking back at. Okay, so the first thing we're going to look at with orientation, the explanation is a little bit different for different substituents. So I'm going to start with the easy one, and that is if you have an alkyl substituent on your benzene ring, which remember we said was an activating group, although kind of weakly activating, but it directed substitution of an electrophile either ortho or para to it. And so what we're trying to answer here is why. Okay, and to explain that, of course, we're going to, and I would encourage you to draw this, by the way, draw this benzene exactly like I'm drawing it. Put the double bond there, there, and there. It's going to make this a lot easier. Okay, and I'm going to put my methyl group right here. That's the alkyl group we'll use. And so what we want to look at is if we react an electrophile with this through a substitution reaction, how can we explain that it ends up orthopara? And so mechanistically, as you know we've done before, I have to look at three different things. I have to look at what happens if the electrophile substitutes ortho, meta, and para. So I'm going to actually write that on here. Ortho, meta, and para. Okay? And then we're going to look at putting an electrophile in a position to substitute at those positions. So I'm going to put in an ortho electrophile, a meta electrophile, and a para electrophile. And then I'm going to show what's going to happen if I do the substitution to the ortho position. Because in that case, it's going to be this double bond right here, this one, that actually reacts out to the electrophile. And so that's going to lead to this intermediate. Where the electrophile ends up at that position, right? And when it does that, there's still an H there. When it does that, remember it leaves a deficient carbon at that position. Okay? I can draw resonance forms for this. And since we're explaining this mechanistically, I need to draw these out. These would be the two other resonance forms because this is doubly allylic, right? So I can move the plus charge to here, which would leave my double bonds there, HE methyl. And I can also move the plus charge out to here. Now again, I'll emphasize the fact that the PowerPoint shows these. I'm also drawing them out so you can see them. So these are the three possible intermediates that can form if the electrophile goes to the ortho position. If it goes to the meta position, it's going to be this one, this pi bond that breaks. And so that means I'm going to have what? The electrophile is going to end up in the meta position with its H, which means my positive charge is going to be there, and the other double bonds remain where they were. And then I can draw the resonance forms for that, which would be moving the plus charge to here. And then also moving the plus charge to where? Right here. And then my double bonds would be like that. Okay? If the substitution is to the para position, then it's this pi bond that's breaking. And when that breaks, I'm going to substitute the electrophile at this position, which means this carbon will be the deficient one, and then my double bonds remain in the same place, at least the other ones. And then I can draw the two resonance forms for that. So I can move the plus charge to here. And so I have that carbocation. And then I can also move the double bond to here, which would leave those double bonds there. My electrophile. And so the question is, once I've done that, and I know that on your computer you can zoom in if you need to get closer in to look at that particular drawing. The question then is, if the reaction is going to proceed to give ortho and para products, what differentiates this pathway, these two pathways, from this one? Because these two must be the pathways that are favored because the reaction directs ortho-para. So can anybody see what the difference is? It's right here, and it's right here. In the ortho and para case, your carbocation intermediate has some tertiary carbocation character, because this is tertiary and this is tertiary. Whereas in the meta case, your carbocation is never on this carbon that the methyl is attached to. So you have no tertiary carbocation character when you go through that meta pathway. So therefore, the ortho and para products are the ones that are vastly favored in the reaction and the only ones you would show. So mechanistically, the explanation with alkyl groups is that you go through an intermediate that has some triple or tertiary carbocation character. All right? So that's the explanation for an alkyl group. But what if we move to other activators? And remember, the general formula for the other activators was the fact that they had a lone pair attached to the atom that is adjacent to the bond. And I'm going to draw exactly the same position for the double bonds as I did before. And then I'm going to put an OH on it. So how can I explain that these resonance activators, like OH or NH2 would work the same way, how these direct ortho and para? Okay, and in order to do that, I have to do the same kind of mechanistic analysis, right? I need to look at what would happen if I substituted the electrophile ortho, meta, or para. So I'm going to put O, M, P. And again, electrophile going either ortho, meta, or para. I put them there so I can show it mechanistically from each position. And by the way, why am I drawing these out like this for you on the whiteboard when it's on the PowerPoint? And you know, we're online teaching. I could just say, look at the PowerPoint. Well, I'm doing this because I'm trying to demonstrate to you how on an exam, if I asked you, why does an OH substituent give ortho-para orientation? I'm showing you the answer right here, where you draw it out. Okay? And so if it's ortho, it's going to be this double bond that breaks. The electrons go out to substitute that electrophile. And so when I draw my substituent, the electrophile is going to end up there, right? Which means I have a double bond here and here, and my deficient carbon is the one to which the OH is attached. And then I can draw another resonance form for that, right, where the plus charge goes to here. And so I have that. And then I can also do what? I can draw one where the plus charge goes to here. All I'm doing is drawing resonance forms, which I know all of you remember how to do and can do. So there I've drawn, just like I did with the alkyl group, I've drawn the three doubly allylic carbocation intermediates that can form. But in this case, there's actually one more. Can anybody see it? Since you have a lone pair on that oxygen, since that plus charge is on the adjacent carbon, I can imagine through resonance moving those electrons in and forming this other additional resonance form. Okay, so unlike the alkyl group that was giving a tertiary carbocation, here with the OH, I'm going from 3 resonance forms to 4 resonance forms. So what does that mean? The more resonance forms you can draw for something, the more stable it is. And so this pathway through the ortho substitution has extra stability. Okay, and so what I need to show next is that going to be true for the meta case? Because if it goes ortho-para, you would think that the meta is not going to have that same ability. So let's see. With the meta, I'm going to break this pi bond and move those electrons out to form the new bond with the electrophile. But here, since it's this bond, my deficient carbon is going to be this one, and I have my EH. Okay? Then I can draw another resonance form for this, where I move these electrons, and I end up with that being the deficient carbon. And then I can resonate that again, where my deficient carbon ends up there. Okay, and is there another resonance form? No, because the plus charge is never on the carbon to which the OH is attached. So I don't get this extra resonance form where the lone pair can swing electrons in. It can't happen. And so there's not a 4th resonance form. Therefore, ortho is a more stable pathway than meta. And by the way, since you're playing the home game, draw out what you get with the para, and you're going to see it's exactly the same as the ortho. You're going to have 4 different intermediates. Okay, so that explains the orientation for the activating groups, both the alkyl and then the resonance donators. That's why they orient ortho and para. So the next thing we need to talk about is the case of meta directors. Okay, so, and the nice thing about the meta directors is they all end up being the same explanation. So it's not like alkyl group being different than the resonance donators. When you have meta directors, they all work basically the same way. And so I'm going to use the example of an aldehyde. I think in that PowerPoint it also shows you for a nitro group, it'll look exactly the same. And so we're going to do the same kind of thing. And by the way, I'm sorry, I instinctively want to draw my double bonds in a different place, but just to make it consistent with what's on the PowerPoint, let's draw our double bonds in the benzene in exactly those positions. Okay? And then, again, we're going to look at what happens if I do my substitution ortho, meta, and para. How can we explain mechanistically that a either inductive or resonance deactivator is going to give me the meta product this time? But I'm still going to set it up the same way. I'm going to look at how the mechanism would be if I substituted to the ortho position, the meta position, or the para position. So let's start ortho. It's this pi bond that breaks. And so the intermediate that forms is going to be this. Okay, so electrophile ends up there. So this is the carbon that's deficient, right? And we should go ahead and say that, remember, in your substituent here, this carbon of the carbonyl is deficient. It's got a partial positive. And the oxygen is a partial minus. Okay. So I form this intermediate, and then I can again draw the two other resonance forms for this intermediate, where the plus goes there, and I have my electrophile in H there, or I can draw this third one where the plus charge goes there. And so I have those three possible resonance forms. Any other you can draw? No, these are the only three. Okay, so that is what the resonance forms would look like for that particular intermediate. Now what would happen in the case of the meta? It must be different, right? Because this is meta directing. So there's going to be some difference between these two. So first, now I'm going to show it's this pi bond that breaks and forms the new bond with the electrophile, showing it now in the meta position. And so when that happens, it's going to be this carbon that's deficient. And then I have my other two double bonds that haven't changed. And then I can draw two resonance forms for this. All right. I can move plus charge to there. Or the last resonance form is where I move the plus charge to there. Okay. So the question is, what is the difference between these two? There's something that makes this one more stable than this pathway. And it's simply this right here. In this case, you have a partial positive for this carbon of the carbonyl that is right adjacent to the plus charge generated in that carbocation. This is a destabilizing effect. Okay, so again, it's not that one of these pathways is more stable, because that would be an activating pathway. Here it's that the meta, this one's, the ortho is destabilized, and so the meta is, just not destabilized. And so it is actually favored. And you would see the same thing if you went through this for the para. You would see that there's a plus charge that ends up adjacent to that group that has the partial positive. And so this goes through meta orientation because this pathway is not destabilized like the ortho and the para are. All right? So mechanistically, we can explain that. And the last one, I'm just going to show you. If you go to your PowerPoint, it's going to explain why halogens are deactivators, which we've already said, but remember they're the exception. They're actually orthopara directing, because what happens is if you look at the PowerPoint and you also look back at the example of what happens with OH, halides have a lone pair on them, so they have that fourth resonance form when they're substituting an electrophile. And so therefore the ortho and the para pathways are actually more stable, even though overall the reaction is deactivated by the halide. Okay? And so I wish at this point I could say any questions, but remember that's what we're going to try to do on Wednesday at 11. Or anytime you want to email me and ask a question about a lecture, you can. You can even direct me to where it is in the lecture, because I can pull up the lecture and we can email back and forth to answer questions. Okay, so that pretty much is everything we need to know about electrophilic aromatic substitution. That is by far the most common reaction that aromatics undergo. So at this point, we've seen the transformations, we've seen explanations for what happens with orientation, if you have one substituent, two substituent. We've seen mechanistically the explanation for why substituents direct to different positions. And now we want to move on to another reaction. Okay, and we're going to call this one nucleophilic aromatic substitution. Now this one is going to be a little different, as you can see from the name. With electrophilic aromatic substitution, we were substituting an electrophile into the ring. With nucleophilic aromatic substitution, we're going to be substituting a nucleophile into the ring. So what does that mean about the reactivity of the ring? We're now expecting it to not be the nucleophile. We're expecting it to be the electrophile. So that changes a lot. But just before we get into this, just know that's not a very good reaction, making the benzene ring have to be an electrophile. So nucleophilic aromatic substitution reactions, you know, there are only a few that will work, and there are very strict conditions for them to occur because they're just not favored. Okay, and so they have very strict requirements. And those requirements are, it must be an aryl halide that the reaction is occurring on. And an aryl halide is, you know, in our case, it's going to be a benzene ring with one of the halides on it: bromine, chlorine, fluorine, etc. Okay, so an aryl halide. And I like to add in here, that's because it's going to be SN1 and SN2 reactions. Remember, those of you that took Organic 1, those were our example of nucleophilic substitution reactions. Well, this is another nucleophilic substitution reaction. Kind of think in terms of SN1 and SN2 because they required an alkyl halide, or at least an alkyl that had some leaving group on it. Same requirement here. Okay? And the second one can only be explained mechanistically, which we'll do probably in the next lecture, because Austin's sitting there ready to set his alarm off, I know. 2, we must have an electron withdrawing group and these are the electron withdrawing groups are our resonance deactivators, you know, the same group of substituents, and they have to be ortho and or para. Be sure to always silence your phone. Okay, and so this one doesn't make as much sense just off the top of your head. This one does. Okay, and so I'm going to show you based on the time. Let's just look at what the general reaction looks like, and then in the next lecture on Friday, we will actually look at mechanistically why we have this second requirement. Because what I want to just show you as an example, and this would be the kind of thing that you'd have on your flashcard, you know, what do the conditions look like for a nucleophilic aromatic substitution reaction. So we have our benzene ring, and based on the requirements, we need to have an aryl halide, so I'm going to put a fluorine on there. Okay, and then we have to have an electron withdrawing group, ortho and or para, to that halide. And so does this meet that requirement? Yes, it does. And so if I have this requirement, all I have to do is react it with a nucleophile. And there are going to be certain nucleophiles we talk about that work well, and an OR minus, which we know we talked about as being a really good nucleophile when we talked about SN2 reactions. That's a good, so you have sodium or potassium, in this case methoxide, something that's a really good nucleophile. So I'm going to actually write nucleophile under here because I know it's been a few months since we talked about the substitution reactions. So I have a nucleophile, and basically what's going to happen, and this is the good news when you watch this, what's going to happen is just like we saw in the SN2 reaction, we're going to substitute the nucleophile exactly where the halide was. So the orientation is much different than what we saw with electrophilic aromatic substitution. Here, the orientation is simply the nucleophile substitutes exactly where the halide was. Okay, and then of course, if you want to keep a balanced equation, you're going to have Kf. And so using terminology we did back last semester, nucleophile and the fluorine here is the leaving group. Remember that term? It's what's leaving in this reaction. And so mechanistically, we have to think about how this is occurring. Okay? And so I'm just going to give some little foreshadowing for the next lecture, because I said that this looks kind of similar to SN1, SN2. And so maybe mechanistically, that's how these reactions are occurring. But if you imagine this drawing is of a flat ring, so I'm looking at that benzene ring like this, and you have your nitro group here, and you have your fluorine here. In order for this to be an SN2-like mechanism, the nucleophile would have to come crashing through this ring, because remember, it has to be that 180-degree, in line mechanism, and this can't happen. So this is not going to be an SN2-like mechanism. The other possibility, well, maybe it's like an SN1 reaction was. But for that to be the case, you'd have to spontaneously lose the fluorine and end up with some kind of carbocation like this. That's not resonance stabilized. That's not going to be how the mechanism occurs. And so next time, we will talk about how this mechanism is actually occurring. And we're going to see that it's actually involves an addition and an elimination step, which if you do an addition and then an elimination, the result is you have a substitution. And that is where we will begin next time. Again, any questions that you're having on the lectures, please, join the conversations at 11 o'clock on Monday, Wednesday, and Friday, or email me anytime. Again, you can take pictures, you can reference the exact position in the lecture that you have a question about, and I'll respond as quickly as I can.